So first of all, I would like to welcome all of you to join for this GÉANT Infoshare. Today we're going to talk about the European time and frequency services and its principal challenges and use cases. My name is Nicolas Quintin and I'm the coordinator of the OTFN projects. And OTFN is part of the GN43 work package 6 on tasks 1 part. And OTFN stands for Optical Time and Frequency Networks. Oh, okay, but first of all, I would like to thank WP3 and would like to thank them for helping us organizing this InfoShare. I would like to remind you that there are public InfoShare every week on Wednesdays that are recorded so that you can watch it afterwards. So I would like to thank GÉANT Partner Relations team that helped us with this InfoShare. Okay, so about OTFN project. So as I was saying, OTFN stands for Optical Time and Frequency Networks. And our goal is to catalyze the emergence of metrological networks in Europe. So about some questions about what, who, when, and how. About the who, so we are people from the NREN community. We are a part of Renater, GÉANT, Chestnut, Psnc, Switch. And we have Xavier, Ivana team, and Suzanne that are here for other coordination teams. And I would also like to thank people from GAR, Uninet, and DFN that have helped us during the first years of the project and that continue helping us organizing such InfoShare and so on. This project started on the 1st of January 2019, and the project is going to last 48 months. So we are halfway to the end of the project. And what are we doing here, in fact? So we are studying challenges for setting up a European time and frequency distribution service. Our original goal was to have test beds deployed in GÉANT network. And we are focusing on holding dissemination events to raise awareness of the NREN community about time and frequency services. And we are also working on missing pieces that would help time and frequency community. So there are several examples. We are, for instance, working on test beds that could gather every time and frequency services so that other NREN can test, for instance, their optical layer there. We're working also in international hub in Geneva and so on. The objective of this InfoShare. So you might be aware that time and frequency community lacks a fiber connection between NMI and the time and frequency end users. And we are here so that you understand the key role of NREN. As you all know, NRENs, they are incubators of revolutionary projects like IPv6, client servers, and cloud computing, but also new type of service such as QKD, quantum key distribution. And we are also talking about spectral sharing, new application for the fiber. And the fact that each NREN is connecting many research infrastructures that can or wants to benefit from such precise signal, from such time and frequency services, that would be a huge boost for scientific collaborations. And that's why it's so, it would be a great collaboration to work with NREN. And another fact is that NREN, they know how to operate huge networks, and that would be a huge help for the scientific community that doesn't share this knowledge. And we want to make sure that after this InfoShare, you understand that metrological time and frequency services distribution in an NREN environment is not only doable, but safe and controlled. I would like also to remind you that OTFN project is now helping GÉANT become familiar with time and frequency services, understanding the phenomena, what's going on, how should I protect my network, and so on. And we would gladly help any interested NREN if you have any question about time and frequency services. So please contact the mailing list in the mail. We're also here to raise awareness of the NREN community, as I said. So we wrote a white paper last year. In this white paper, you'll find, I hope, exhaustive info about characteristics of ultra-stable time and frequency service distribution. Like what are the main time and frequency elements in a network? What are the existing techniques? We are also discussing about how we can implement time and frequency services over NREN networks. There is a huge discussion about the wavelengths, the lead time to service deployment, performances of each technique, so that you can really understand how to match your end users' requirements on what you can offer them through your network. About the future events, so OTFN intends to host next InfoShare in the future, and the last presentation of today's InfoShare will be about defining this next InfoShare with you, what the community is asking for, and how OTFN can help you with time and frequency. And we also plan to have trainings, workshops, and so on. I mentioned the international hub that we intend to have in Geneva. So just a quick summary of the situation. So we are willing to have several interconnection between NRENs in Geneva. So why Geneva? Because we have Renata fibers as well as Psnc switch and softnets that have fibers connecting to Geneva. And directly connected, we would have Chestnut and GAR. And we also have gateways to Nordinet and GÉANT in Geneva. So that would be a great place to interconnect the different NMIs. And we all know that there could also be potential end users looking for a very precise time and frequency services for certain experiments. So that would be also a good thing to go there. Okay, so just a couple of remarks before we start this InfoShare. I would like to please mute your mic during the presentation. So thanks for starting already. Do not hesitate to write your question in the chat during presentations. Do not interrupt speakers unless they agree to do that. And at the end of each presentation, we'll have a couple of minutes to ask your questions. And also if you want to say something. And as we want this InfoShare to be as interactive as possible, really comment, well, your feedbacks are really valuable for us. So do not hesitate to intervene, yeah. And finally, we hope you'll enjoy this InfoShare. So about today's agenda, we split the InfoShare into 2 sessions. So the first one will be led by Christophe Turza and will be about the requirements, use cases, and European projects. And in the session 2, we will describe the current situation in NREN Networks, describing CLONETS-DS and TiFOON projects, and some example of time and frequency services implementations. And we'll finish with a Q&A. So Christophe, I'll pass it over to you for your session.
Thank you. Good morning to everyone. I'm pleased to lead the first part of today's InfoShare session. The topic we are going to present European time frequency service, especially in context of the fiber networks. It has been widely discussed for at least several years now on many forums. However, it still has not been widely implemented both in Europe or worldwide. Nevertheless, it has to be said that the transfer of ultra-stable time frequency signals through optical fiber networks is most dynamically developed just in Europe. So it's a big chance for us. However, this transfer is not as simple as in other types of typical transfers. It's mean data transfer. There are some specific requirements to be met, and because many commercial operators do not take up this type of challenge. So this is a great opportunity and place for NRENs and GÉANT to extend its offer with a new kind of service or even a group of service, because we are talking here about several varieties of them. So these services are still not widely available, and this is the best time to take initiative in this area. I realize that the issue discussed here may seem be very difficult in some areas and complicated to some people. So I'm very glad to that our invitation was accepted by Mr. Harsh Nas from PTB, which is a German National Institute of Metrology. Harald is the head of PTB's Department of Quantum Optics and Unit of Light since 2011. Due to the fact that he has been actively involved in the distribution of optical frequency standard for many years and actively support all initiatives to build a pan-European network. He has extensive and in-depth knowledge on this topic. I think that the topic presented by him will be excellent introduction to the issues discussed today. His talk today is entitled Why Optical Time and Frequency Service is so popular. So we will be glad to, so we will give voice to our first presenter and speaker, Mr. Harald Schnatz. So Harald, can you present?
Yeah, okay. Thank you very much for this kind introduction. So let me see, can you see my slides?
Yes.
Yeah, okay, great. Yeah, thank you very much for the opportunity to give us a short introduction here. Actually, at the beginning, when Voivod invited me, the task was to talk about problems to be solved and use cases. So, but later that changed into why our optical time and frequency services are so popular. And I want to start with this part of the story, actually. And well, either that is a talk by itself or it's a simple answer. And I try to give the simple answer because frequency is the most precise measurable quantity. In other words, whatever you can turn into a frequency measurement will be not limited by this measurement itself. And that was something, for instance, that Art Schawlow actually advised his students, never measure anything but frequency. And one of his students was Ted Hensch. And to make the long story short, you all remember that Ted Hensch was awarded the Nobel Prize for the invention of the frequency comb, which actually translates any optical frequency into radio frequencies, which can easily be measured. And this is the key element for the NMIs when we talk about frequency measurements of any optical clock currently under development. Well, to make the long story short, the comb acts in three ways, actually. It can either measure an optical frequency with, it can multiply a microwave frequency up to the optical domain, or compare optical with microwave frequencies. You can put it the other way around. You can take an optical frequency at terahertz, 100 terahertz whatsoever, and use the comb as frequency divider, and then generate microwave frequencies with unprecedented performance. Or, and this is the case when we are talking about optical frequency dissemination, we can compare optical clocks using the comb in a way that only the optical clocks itself contribute to the uncertainty of the measurement. And if I can compare two optical frequencies with each other, then I can also use the comb to stabilize a reference frequency within the comb spectrum that has the same performance as the reference. And this is the key element for disseminating optical frequency. Sorry, this is somehow got lost by transferring it into the PowerPoint slide, PDF slide. So if you consider you have an NMI that has optical clocks or cesium fountain clocks, then you can use the frequency comb, as I said before, to imprint this information onto a laser, typically at the telecom wavelengths at 1.5 micron, to disseminate this frequency, and you can imprint reference frequencies in the RF domain, for instance, 10 megahertz, 100 megahertz, whatever you want, and for instance, a time scale. Now, if you disseminate that using optical fibers, all you have to do on the other side is to reverse this imprinting, and generating from this 1.5 micron that you have transmitted over the network to generate optical reference frequencies, or again, timing signals or RF signals. So the key point actually then is, or the task we are discussing here is actually, how do we disseminate the information from the NMI to an end user without introducing additional error by the dissemination tool. And I will just give you a brief idea about how we do that, especially for frequency transfer. So typically, as we have talked right now, the transfer laser is at 1.5 micron, which is by using the frequency comb locked to, let's say, an optical or a microwave reference in an NMI. If we send this line, this laser light down to a fiber, then this doesn't really work out here. Nevertheless, at the output of this fiber, the frequency will be unstable because perturbations occurring along the fiber link. To compensate that, we take a partial reflector and send part of the light back to the input. So what comes back there contains more or less 2 times the fiber noise. We can measure that by using a by setting up an interferometer where we have a short arm as reference arm and the fiber acting as the long arm of a Michelson interferometer. So we can measure this noise here by heterodyning that with the input light. Now, if we don't want to have that at 0 beat frequency, we typically introduce an acousto-optic modulator that shifts the frequency that is launched down to the fiber by some amount of a couple of megahertz. In order to avoid or discriminate any stray reflections occurring along the fiber, we typically insert another acousto-optic modulator at the end. So the beat frequency we are obtaining here is typically at the frequency, either the difference or the sum frequency of the acousto-optic modulators here. And it can be shown that if we compensate the noise by steering the frequency of the acousto-optic modulator, we can get rid of the noise also at the far end. This is the key element to any frequency dissemination using optical fibers. But we should keep in mind that this scheme requires fully bidirectional operation, because the light that travels through the fiber and is then on its way back heterodyned has to travel the same path to avoid any uncompensated fibers. This scheme, or the now I want to discuss some problems to be solved and use cases, but I would like to turn it around and would discuss use cases first, and then in the final slide tackle the problems I see that have still to be solved. The principle of this scheme I propose now has been extended or measured for many, many years, and sophisticated techniques have been developed, and the limits have been pushed further down from initially something like 2 times 10 to the minus 16 now to limits at 10 to the minus 21, exceeding the best optical clocks by orders of magnitude. The original, our motivation for the NMIs was actually the question if optical clocks outperform, as can be shown in this slide here, optical standards outperform the classical cesium fountains by at least 2 orders of magnitude or even more. The current means we had to compare distant cesium fountain clocks were mitigated typically by satellite techniques. So the GPS carrier phase typically would intersect the instability of the cesium fountains at typically 10 to 5 seconds, which is 1 day. So at 1 day, the instability of the GPS carrier phase method falls below that of the cesium fountains. If I would like to compare optical clocks with GPS, then I would have to measure forever, basically, because this line goes down here and would intersect at, I don't know, months typically of measurement time. And if as the instability of the optical standards is now approaching 10 to minus 17 at 1 second rather than the 10 to minus 14 now up here, that would take, it's more or less impossible. So we were looking for different ways. And the only way, as we see it, to compare such optical clocks over large distances is using optical fibers. So this gives you just a quick overview about the last 15 years or so, where we started to tackle this problem together with the colleagues at NMIs in Europe, and in close collaboration now with the NRENs like DFN, Renater, and GAR in Italy, Psnc in Poland, and so on. I could go on mentioning those things. And for instance, here we have the GÉANT 3+. That was the first collaboration with GÉANT, offering us the possibility to establish now the link between Paris and London for the comparison of the optical clocks. And the story goes on and still continues. And currently we are in this state where the Ampere project TiFOON and the CLONETS-DS is now active. And we will hear a lot more about this in one of the next talks. So what we can say is that was one of the first demonstrations that optical fibers really can help to measure or compare optical frequency standards. And that was one of the first where we had this 900-kilometer link between Braunschweig and Munich or Garching at MPQ in Garching, close to Munich, where we could show that we really get the instability down into the 10 to minus 17 level and further on. So optical fibers, together with the optical standards, make new time and frequency transfer capabilities possible. And I would like to give you just a few ideas about what we can do once we have the clocks, once we have the fibers. And of course, the first one is what I already mentioned. One of the typical issues for NMIs is clock comparisons. And this is just an example where we compared for the first time the clocks at PDB and the ones at CERT in Paris, demonstrating that really the clocks agree within the 5 times 10 to minus 17. And we get the instability down to the 10 to minus 17 level in a couple of minutes. We can use it for precision measurements where we use the standards at PDB, for instance, to measure the hydrogen, the 1s, 2s transition in hydrogen. We can disseminate, as shown here in this slide, ultra-stable laser light from one place, here in case of CERT, to the LPL in Paris to perform precise high-resolution molecular spectroscopy. We can demonstrate that we can use it also for time dissemination and to get better time scales, as shown here. Typically, we can get the timing jitter down to the picosecond level, where the GPS timing jitter is rather at the 1 nanosecond level. We have demonstrated that you can get the accuracy down to the 10 to 30 picosecond level over extended periods of days or weeks. But there is also more. You may remember, so what is currently discussed is, can we use the timing signals provided over the optical fibers as a backup system for GNSS? And probably you have been aware of the fact that Galileo had some significant failures, and as all navigation transport depends on GPS and its and the systems like Galileo or Beidou, it's essential for our today's infrastructure. Recently there has been a US executive order that stating that GNSS is vulnerable to spoofing. So NIST now takes action to set up a backup system between Gaithersburg and some other places in the US. One of the stories that really makes clear how timing may affect also fundamental things is the question you probably have all been aware of, are the neutrinos faster than light? And the long story was, to make it short, there was a miscalibrated GNSS receiver that originally triggered this question. So timing is essential. There is the financial, the MiFID initiative or directive of the EU stating that you need timestamps for financial, don't know the word, you know what I mean. So time distribution is also critical for the critical infrastructure like power grid, security, finance. And there is also the synchronization issue on mobile networks, and that was one of the slides Helmut Imlau showed us at the last TiFOON workshop, where the idea is that the primary clocks that operate have to be operated in mobile networks should be interlinked by optical fibers to provide the redundancy in case of GPS failures and so on. So from time and frequency issues related to NMIs, that goes down well to the production level here. But there are also other applications like test off. Sorry, here happened something. Yep. Sorry, I have to. So that is fundamental constants measurement or tackling this question for fundamental theories. Testing Einstein with clocks, so local position invariance while the Earth spins around the sun, or the search for dark matter if the clocks would be affected of a domain that moves through the Earth at different timescales. So that are tests of fundamental theories. More recently, people came up with the idea to use the clocks for geophysics. And Bondarescu et al. Discussed the possibility that you could measure, for instance, the inflating magma chamber below the Etna, placing a clock close to the Etna, connecting it with a fiber and to a far distant clock. So any inflating here would change the frequency of the optical clock. You could measure solid earth tides if you separate the clocks and so on. There was a demonstration that you can use the fibers to detect, for instance, earthquakes. There will be a talk later by Paul Bulven talking about applications in the VLBI, and here's just the example that Torino, our Italian friends connected Torino with the VLBI stations in Medicina and Matera, heading towards Sicily and so on. And one of the more recent applications is that we use ground-based atomic clocks in geodesy, making use of the gravitational redshift, where in this demonstration we put the transportable strontium lattice clock of PDB into the Modane underground lab in the Alps and measured it with respect to the clocks in Torino, demonstrating for the first time that you really can use the gravitational redshift to measure height differences. And in the long run, that would enable us to unify height systems that currently differ at the level of 0.5 meter in Europe. And if you place clocks at certain places here and interconnect them, then we could unify those height systems. These are just the applications I wanted to briefly discuss here without going into much details. And now let me come to that point. What do we really need for this? So the requirements for this infrastructure is that we need a transmission channel or a dark fiber. We need the bidirectional operation, and we would like to have fibers in the underground conduct to get a good seismic and thermal isolation. We need some low back reflection connectors. We should be able to implement our dedicated equipment into intermediate huts along such links. We should have access to the containers, and the signals we are currently discussing that should be sent is an optical carrier, at best at channel 44, but any other will do. And to also disseminate timing signals, we would use amplitude modulated lasers, for instance, 12 or 25 gigahertz apart from the optical carrier, and would generate a timing signal. So the problems to be solved, to finalize, what do we need to do? We need sustainable access to dark fiber or a channel. We need to assure the traceability to the SI system for the signals that have to be transmitted. We need redundancy. We need interoperability throughout Europe. We need a good management of the network. And this is probably the key point for the involvement of the NRENs, because you have the experience about that. And we need stakeholder involvement. So all these things I tackled just briefly are the top level applications we can currently see, but there will be many, many more in the moment such a network gets established in Europe or even worldwide. And the most pressing situation or problem is, how do we find sustainable financial support? Because we do not want to have such a network on the next 5 years basis, but on a long lasting basis, because the effort to establish such a network is quite substantial. And with this, I would like to thank you for your attention.
Thank you very much, Harald, for this interesting presentation. And I think we have only a few minutes for a brief discussion. I see Konstantinos, would you like to raise a question? Konstantinos,
I apologize. This was this was clapping. I like the presentation.
Sorry. Is there any questions to Harald from your side? Maybe in the meantime, I will ask you because you discuss here a lot about the international discussion and international connections. How NRENs can, in your perspective, how NRENs should communicate with research in NMIs institutes? Because in my experience is that language is common language is very difficult to establish between NMIs and national institutes. So who can support NRENs in such a discussion?
Well, one of your platforms actually here, the OFTN, is the right platform with respect to the NREN community. On the other hand, we have the Ampere project, where now more and more NRENs get involved learning our language. So instead of, if I think about the future, it might be worth to consider not to have separate tracks there, but to unite those into a single track, so that we speak the same language, we address the same stakeholders, and the same financial support.
Okay, thank you. Any other questions? So one more time, I would like to thank you, Harald, for your presentations, and we can move on, I think, the second talk. We would like to give a voice to the NREN representative now, Mr. Jani Meri from FUNET, Finnish IT Center of Science, where he has been working since 2009. He's currently mainly involved in designing and planning the optical part of the next generation FUNET 2020 network. His presentation today is entitled Time and Frequency Service for End Users, so we can expect some more practical information from NREN engineering point of view about such service implementation. So now we'll give voice to our second speaker, Mr. Jani.
Thank you for your introduction, and I have to admit that my point of view is from NREN Networks side. I'm not an expert in time and frequency domain like the previous presenter was. So I will go through some of services we have built in last, let's say, almost 10 years now in Finland, and what kind of issues and challenges we have experienced. Our, let's say, first view to time and frequency transfer started in 2011. We got the proposal from Sweden to build a time link from Stockholm to Espoo, and that was a holiday period, so we didn't have any person to answer correctly, so we said yes, and it was built. It based on STM64 transponders. We did not use anymore, and that link was online for 4 years. It even survived the upgrade to coherent system, but it was very complex and required a specific equipment. But it was a very good thing for us because we got some insight to what kind of requirements we could see from the time lab people and from our researchers. Next thing was just after that, we discussed with our national time lab to build a similar link in Finland to connect to clock sites in Espoo and Kajaani. And the technology what they have been looking for was PTP wide rapid. It was designed at that time to be used maximum 10 kilometer links originally in CERN, but the route what we would like to use, that it was almost 800 meters. And we asked from our optical vendor, do they support that? No, they still gave us an alien wave into the system. We bought some optics, plugged it into the system, and it worked. Of course, required some software changes because the wide rapid switches were expecting that kind of latency we saw. But it was easy start for us. This is some kind of schematic representation of what was the original setup. So we had an old system with dispersion compensation. We actually moved the same setup to our new system, which is without CD compensation, and it seemed to work 800 kilometers. That was some kind of surprise for us, but it was easier than thought migration. There is some measurements what our national time did over the link. Also some issues due to fiber cuts and unidirectional structure. But that was easy one, and after a few years, we started looking for directional time and frequency transfer, which is the preferred version for the end users. We started in the metro area in Helsinki to use basically CW filters and the wave transmit wavelengths on both ends. Also worked without any problems. That was shifted later to DW filters, which gave let's say better quality for links, and that's actually what we currently using mainly when we run any metro timings, and all of these implementations based on PTP wide, which we chose on very beginning. With the newest addition here is the directional optics we got from ADVA, which shift the CWDM use case from two channels into the one channel. So the wavelength difference is smaller. Few implements we are running. This is very basic thing. We feed a reference to our NTP server within the Helsinki region based on ADVA optics and filters, which are chained. This is chained to other filters we use for OTDR. But the same optics is actually used on later slides for our aim to run it over even longer distances. Second, let's say most important link we have for time and frequency transfer is from Espoo, from our national time lab to Metsähovi observatories. There are two observatories, Aalto University Radio Observatory and Finnish Geodetic Institute. Both are using these services. So we did the split few years ago for this fiber to give the bidirectional setup for time and frequency transfer. One fiber was rerouted to the time lab, and we use remaining fiber for data traffic. And that also have worked well. And now we have some plans to renew those filters to add even more channels to the fiber. Basically 1610 to support those ADVA optics and maybe L-band DWDM optics and OTDR. And there are some plans for ultra stable laser setup. I got this text from the expert from the National Time Lab, so I don't go to the detail because this is very much beyond my understanding. The filter setup is very simple. We bought this from Fiberstore. It's customized version where TX and RX are using either even or odd channels. So it's 100 gigahertz channel spacing for each. Seem to work because this very this passive system and still quite short. The testbed itself is run by VTT. They do have wide rapid switches and some other things in Metsähovi and Otaniemi. The bidirectional part is basically the line fiber, and until that is connected to the filters, and there's only short dual fiber linked to traditional DWDM optic. So it's pretty much bidirectional setup from end to end. There are some results. I will skip these and go to the next slide, which is used to when we made discussions with the Finnish and Swedish time infrastructure operators, what kind of solution we should use for long haul transfer links. There are currently two approaches to use this bidirectional optic, which is very easy to do because it's building bidirectional optic, and another approach is to use L-band DWDM optic, which with the optical circulators splitters, which will give a better symmetry, but it requires more work and calibration, etc. So that's a way to go to the long haul transfer. We had discussion with the National Time Lab how to implement this. The obvious way would be to use dedicated fiber, but it's very difficult, pretty much because of cost. Nobody has, or it's very difficult to get funding to acquire REN fiber. So our focus was to look for filters, what we can install the existing optical systems, some kind of sideband filter which give access to spectrum. And there's also two different ways to do, either use regeneration or bidirectional amplifiers. And we chose regeneration because it's the easiest one. Amplifiers seem to be a little bit problematic to find good equipment, cost-efficient way to implement, especially if there are multiple hops. So our experiences will or based on currently on sideband filters and regeneration. Other challenges when you try to integrate time and frequency transfer to optical system, we use a lot of Raman amplification. I think 2/3 of our links are using Raman amplifiers, which will cut out some parts of spectrum. The first thing is, of course, is that you can install filter in front of Raman amplifier, so it has to be behind it. Wavelength shorter than C-band won't pass the Raman amplifier, or there's very high attenuation. There's some insertion loss for signals which pass the amplifier, but we also get some Raman gain, even in 1610 region. We get that also for 1650 nanometer, which is our OTDR system use. So we choose 1600 region between C-band and OTDR. It's a little bit higher loss per kilometer and higher dispersion, chromatic dispersion, but it seemed to be good compromise. There are optics, CW optics, or for that, and also some L-band DWDM optics for that region in the spectrum. Originally, we did daisy chaining different filters, but that was thought not to be an optimal solution. So we started to plan how we can implement it a clever way. And we had extensive discussions with our Swedish colleagues, Sunet, and both Swedish and Finnish time-lapse and organization could be the national time infrastructure and our optical vendor, which is same for both. And 1610 was chosen. We did test with the ARPA optics using normal CW filters. Our colleagues in Sweden found that L-band optics should be available. A little bit difficult to do to buy, but there are, even with the required chromatic dispersion tolerance. So that end up that we would have two options to use the ARPA optics and DWDM. Also, there are some problems in the C-band. EDFA noise is filtered out, and there should be only minimal Raman noise on that region. We tested both with this wide rapid switches and low latency jitter media converters. But more examples in later slides. We did optimization for the filter, so all of our requirements were built into the same filter, custom built. So we have C-band access, time and frequency access, and OTT access, and for DWDM L-band system, we also ordered some customized optical circulators, high loss links, and splitters for medium loss links. Those were very cheap, so pretty much no issue at all. Filters in the systems are placed depending on amplification structure. So if I use EDFA only, the filters are in front of the booster. But if we need to use Raman amplifier, the filter in incoming direction would be behind the counter propagator Raman amplifier. So it will, all signals will pass basically the Raman amplifier, and the signals will be handled to either the optical circulator splitter and then to the wide rapid switch or media converter. Bidirectional optics system is a little bit simple because we can directly patch the filter to devices. This is our implementation. We are planning to install next few weeks in Finland between Kajaani and Oulu. Will base on 2R regenerator cards on ILA sites and wide rapid switches on ROADM sites, and it will offer two channels to both directions. So it will have also a return channel from for example from the clock side. End users and requirements. What we have seen in the past and regarding what kind of users we might have for these links. The first obvious user is this is national time lab, but they do collaborate with the research infrastructure. So usually there is the national time lab and some other user involved. And in past we had the link to Sweden, hopefully also in the future, which will connect the other time labs in other countries. But there are also some other potential use cases. We have bigger research infrastructures. We have universities in Finland. Very few use cases. I know actually one, let's say, a research specific user which will use our wide rapid network to synchronize 5G mobile base stations. Industry, potentially there are users, but have to say that we have not seen any inquiries regarding that. And national time infrastructure, which let's say quite many seem to have let's say opinions that it should be built, but the problem is that very few have sustainable funding available. And how we work with our end users. I think the first thing is collaboration with time-lapse and research infrastructures. We started when we built the first link to Sweden and got in touch with correct people, and we got a lot of feedback and their requirements, how they want to use our optical systems. And that was a good thing when we prepared our network renewal a few years ago. So we know beforehand that we should be able to support optical time and frequency transfer. We did not know how it would be done, but there is need to do it. And we required support without tender from the vendors for alien waves and sideband access. So it won't be a surprise for them when we go with the further details how we will want to build it. Another thing, what I personally like to do is standardize these things as much as possible. But if there's need to change it, you have to be open to do it. And also, if it's reasonable, the support for this kind of application should be built from the very beginning, day of one, because it's easier and cheaper to do that way. And one small technical detail, motor ROADM systems, which have dual WS modules, it will help with at least with the unidirectional signals, because you can just plug in the systems into ROADM and don't need to have any specific filters to filter out other channels. Service models, that's a difficult part. When we started our work with our national time, but they were not our customer at all, which was first problem. Had a lot of discussions, could we serve them or not, but that was solved years ago because they joined to us, our customers. But still, it's difficult when this kind of services need to be built, because it's very customized system built for one customer. So there is no such kind of time and frequency service in NREN's service portfolio. So you have to be creative when you answer to these questions.
Can you have 1 minute?
Yes, I have 2 or 3 slides. So what we are planning to or aim to or hope to do in the future, I think there was a discussion to re-establish the link to Sweden again, using these new technologies, maybe link to Estonia, a research site in north, where we have a big infrastructure, what we are planning to support on network side, but also we might be able to provide them also time and frequency. That's not clear yet because there are a lot of moving things, but I think that will be discussed in the future. And the last slide, the current status in Finland, our services we currently running, what we are building, and there's some possibilities to extend in the future. Okay, thank you.
Thank you, Andy, for this very interesting presentations. I've seen on the chat one questions. If the lasers which you're using for 1605 and 1615 are thermally stabilized or are typical?
Yeah, I think Ragnar can answer that question better than me.
Okay.
And
Harald, I see you have a question.
No, not a question. Actually, just a comment. And I think this is a great success story that actually started within one of the European metrology programs when we were looking at possibilities to, at that time, we talked about low-cost dissemination of optical frequencies, and we came across the first workshop we had. We came across the White Rabbit, at that time just established for the CERN infrastructure, and just 10 kilometers or something like that. And it's really great to see that White Rabbit now evolved to this long haul dissemination, triggered in Finland or in the Netherlands, actually. So in my point of view, it's again, a very good example for the collaboration between NMIs and the NRENs.
About the low cost, actually, those optics are quite cheap. They cost a few €100. Repeaters cost something like 200. So it's very cost efficient way to do it. And we will see how good it will be when it's up and running. But seem to be at least a good option. Might not be the best one, but
may I
maybe I have one. Yeah.
May I add another question? Do you have a clear indication what your customers are really need? I mean, you started the implementation of the White Rabbit, but and it looks like they are totally happy with the performance they can get via White Rabbit. But are there other more demanding applications you are aware of that might be a good feedback for the CLONETS-DS consortium to take into account?
What I've heard, I think the users which have been in touch with this implementation have been happy with the performance. Mm-hmm. But, again, I'm not an expert in this field, so.
Okay.
But when we ask from the research project, what is the accuracy they will require? It's not really strict, to be honest.
Okay, I think time is running, so we have to speed up a little. So we have to move this conversation to offline, and when the last session at the end, or last presentation in this part of the session, we would like to give a voice to representative from Research Institute named Paul Boven, which is a physics or also network specialist from GIVE. So he is a person who knows very well the subject of time frequency transfer from both sides, the end user and the network operator, or a person who implements such services in the network. So Paul, we're giving you a voice now.
Okay, can you hear me?
Yes.
Good, and can you see the slides?
Yes.
Wow, that's going quite well already. Hello, my name is Paul Boven. I work at GIVE, the Joint Institute for VLBI ERIC, and we're located, not sure if you see the pointer, but we're located here in the Netherlands. And as you can see, European VLBI network is actually a bit larger than Europe these days. There's a good reason for it, because we do radio astronomy, and the resolution that we get depends critically on the distance between all the participating telescopes. So radio interferometry is a technique where you make like a virtual radio telescope consisting of many telescopes that observe the same source at the same time. And the resolution depends on the distances that you can achieve between the dishes. And for VLBI, it can be as large as the whole Earth or even beyond that, where you're using spacecraft. And the higher your observing frequency, the shorter your wavelength, your resolution also goes up. And what we essentially do is we measure the phase and the delay between the signal received at each of the telescopes. And applying a lot of mathematics, you can actually turn that into an image of the radio sky. To do this phase measurement, you need to have the same reference clock at each telescope. And on a smaller scale interferometer, like the Westerbork Synthesis Radio Telescope or the VLA in America, you can use distributor clock over fiber. But once you build out an instrument over the whole world, so far the only solution has been to use to equip each station with its own hydrogen laser. And due to the enormous baselines and the high observing frequency, we achieve basically unsurpassed resolution well below 1,000th of an arc second. So the stability requirement, I'm just going to get through this briefly. This is not a full analysis, but just to show what is roughly required. Say you're observing at 10 gigahertz, so you have a period of 100 picoseconds, and you want to integrate over 1,000 seconds. So you want to observe over 1,000 seconds and add all these integrations together in phase. So your phase has to be stable to within a small fraction of that 100 picoseconds. And we can do that for about up to 1,000 seconds. By that time, the turbulence in the ionosphere or in the troposphere starts to reduce the coherence, and we have to use different tricks. And to reach 1,000 seconds at 10 gigahertz requires an Allen deviation on the order of 10 minus 14. And that basically so far required using an active hydrogen laser at each of the radio telescopes. Now, we actually want to observe even longer, of course. And to mitigate against all the ionospheric effects, we have all these telescopes pointing at the science target, and then a compact radio source to recalibrate, and then back to the science target, and then back to the other in a very quick cycle of just a few minutes. And that takes out the ionospheric variations, but also any drift and anything in the frequency references. At the start of each observation, we have to line up the array, phase it up by having all the telescopes, again, look at the compact, strong source to calibrate the drift that has happened on all the hydrogen lasers since the last observation. So I would like to talk about the Asterisk Project, which is a demonstration project that we did in the Netherlands between the, oh, I've lost my cursor now, sorry. Between the Westerbork telescope on the left and the Dwingelo telescope on the right. So the Westerbork synthesis array is 14 dishes, 25 meters each. It's owned and operated by CLONETS, member of the European VLBI network. And of course, they have their own hydrogen laser. Sorry. The Dwingelo telescope is sort of the precursor, much older. It stems from 1956. It is no longer in scientific use, but these days it's operated by volunteers. And I happen to be one of them. And of course, it doesn't have a hydrogen laser because these things are pretty expensive. And between Westerbork and Dwingelo is actually 35 kilometers of dark fiber. And we also built a 169 kilometer link using the SurfNet infrastructure, which is a production DWDM network that we managed to piggyback onto with our White Rabbit-based timing service. So to do this, we had to do some improvements to White Rabbit. We used the low jitter data board from Metrology. We also used the cleanup oscillator to get the short time phase noise even better. And of course, we use DWDM stabilized SFPs. And that also means that you no longer are talking about bidirectional SFPs, but they actually have an input and output port. But then we use an optic filter to combine them into one single fiber. So to make White Rabbit coexist in a DWDM network, we did the following. On the left image, you see a standard amplifier HUD with two S-phase, one for going to the east and one for going to the west. And they have a filter in front of them to break out the so-called optical supervisory channel. And these filters basically break out everything what is not in the C-band. So we made use of that by adding additional filters to split off a completely different wavelength that we used for White Rabbit. And that way you can actually install these and you only interrupt the OSC, but you're not actually interrupting the service running on a channel, which is pretty important to the actual owner of the network. So we did this in two locations. As you can see in the graph, we're using a completely different wavelength for White Rabbit as for the optical supervisory channel. And SurfNet is using in SurfNet 8 the ECI brand of optical equipment, which basically just supports this out of the box. Because we're outside of the C-band, we cannot use EDFAs. So amplification was actually done by silicon optical amplifiers or semiconductor optical amplifiers instead of using EDFA. And that way we made bidirectional optical amplifiers for the White Rabbit signal. So the link in total looked like this. On the right hand at the bottom, you have the Westerbork telescope with its own hydrogen maser. From there, I still don't have my cursor for some reason, sorry. From there, we went north to the city of Groningen, where we had an optical amplifier installed, a bidirectional amplifier at the SurfNet node. And from there, we went back to the radio telescope in Westerbork. And from there, we went to the Dwingler radio telescope. But we also had the more direct path where we just used 35 kilometers of dark fiber and we used simple C-band DWDM SFPs, so we could compare the two. Another goal of this was to connect the LOFAR radio telescope, which is also located in the north of the Netherlands. And this is a measurement of a link performance, where we basically went from Westerbork north to Groningen and back. So basically we have the hydrogen maser, we go up the link, down the link, and we measure the difference. And there's a lot of colors in this plot, but the important lines are the red one, which shows the LN deviation when you measure it like 100 times a second. And then the blue line is when you measure it like every second. And you see those two lines basically connect. And the black line you see in the left image, in the ADEV image, is basically the LN deviation specification of a hydrogen maser just from a factory brochure. So maybe take it with a grain of salt. But what you can see is that over most short time scales, the link is about an order of magnitude worse in ADEV than a hydrogen maser, but at about 10,000 seconds, we actually start to get below that stability. So what we ended up doing is doing VLBI observations, and what you see here is the LN deviations not measured on the link, but actually measuring the phase by looking at the compact radio source. And we've done this twice, or at least in this graph, we're showing it twice. Once on the 35 kilometer link, which is just simple DWM optics, and once over the 169 kilometer link, which includes two optical amplifier. And there isn't really all that much difference. And for only two measurements, I can't really say that the one or the other is better. You can also see that beyond a few hundred seconds, the phase stability starts to get worse. And that is basically just the changes in the ionosphere that are starting to affect the signal, which becomes different in phase between the two telescopes. Another application I want to mention is LOFAR, the Dutch low frequency array. So I already showed that LOFAR connects to the Westerbork maser, and in LOFAR 2.0 upgrade, this is going to be rolled out to all the LOFAR stations. So this is work that is being done right at the moment. And White Rabbit is definitely good enough for LOFAR because the observing frequency is so much lower, and the required stability depends on the observing frequency. The other advantage of doing this is that at the moment, every LOFAR station, and there's like 38 Dutch LOFAR stations, they all have their own GPS-locked rubidium clock. And that has caused lots of problems with actually making the images because the phase does unpredictable things as they synchronize to GPS. But also, they in the field, without much air conditioning, etc., they tend to have a pretty high failure rate. So those are two major reasons for replacing all these separate atomic clocks with White Rabbit links. And we hope to get a really significant upgrade to the image quality out of that. So time and frequency distribution is already happening in VLBI. So apart from the Asterisk project, which was more of a demonstrator, there's two systems already in use. There's the Polish LSTAP system, and they are connecting 2 of their UTC labs in Poland, and another lab that has its own strontium clock, and they're connecting to the TiFOON radio telescope. The TiFOON radio telescope has its own hydrogen maser, so they were able to compare the VLBI performance using a local hydrogen maser versus a remote maser. And because the frequency stability of the link is so much better than the hydrogen maser, they could not see a difference. But what they also did is they used a comparison between the local hydrogen maser and a remote strontium optical clock. And that really gave VLBI an improvement in RMS phase noise. It was not huge because you're still doing VLBI against stations that are only using a hydrogen maser, but there is a bit of room for improvement there. And the other thing, it is actually in operational use because they've used it to replace their aging and failing hydrogen maser, which is an issue actually at several VLBI stations. The Italian system called LIFT, a link for frequency and time, uses coherent optical transfer from NREN, which is their UTC lab, and they have hydrogen masers and cesium founders and a terbium clock, I think. And initially they connected to the Medicina radio telescope, which is 550 kilometers, and then also to the Matera radio telescope, which is 1800 kilometers. And again, they compared the local hydrogen maser versus remote hydrogen maser and could not really see any difference in performance. And they were able to do 2 radio telescopes on the same clock. And they are in process of expanding this to the Noto and Sardinia telescopes as well. So finally, just a brief summary of sort of what the requirements would be for VLBI time and frequency distribution. Well, as we're talking to an NREN, an audience, half of which is involved with NRENs, one of the things you need is network bandwidth, and most of the VLBI stations have that these days. So there is already a fiber connection. At the moment, we're mostly observing at 2 gigabit per station, and probably this year we will increase that to 4 gigabit, and further increases to 8 and 16 and even 32 are already being worked on. So the frequency stability you need is basically at the level of a good hydrogen maser or better. Of course, if you're observing at lower frequencies, you can get away with lower stability. And we've seen some hints that lower Allen deviation can actually improve the sensitivity. But in the end, we're going to be limited by ionosphere or troposphere. Now, the timing accuracy we need for VLBI is not terribly critical. As long as everything is in phase and stays in phase, then within 1 microsecond or so, we can easily phase up the array and then just take it from there. But there are other use cases in radio astronomy, such as pulsar timing, which require much stricter timing distribution, and that might be something you might be interested in looking into. You are basically competing against a local hydrogen maser. So what would really make this interesting is better performance, but also comparable availability. So that really means things like redundancy, so that a single fiber break doesn't take your whole observatory down, because once you don't have the clock, you cannot do VLBI. And you want to have some performance monitoring, which you can probably best do if you have 2 signals coming in from different directions and you can measure their relative ADEF, which can only be good if both of them are working. And finally, well, all these radio telescopes are in pretty remote locations. Like I said, some of them already have optical connections by now, some of them still don't or have very low bandwidth. And of course, getting an actual optical carrier there is even more of a challenge, but radio telescopes have to be this remote because cities and industry just create too much radio frequency interference. So there's always still a little bit of a last mile challenge, although that is getting close to being solved now. So that's in a nutshell what you would need for VLBI and time and frequency distribution. Time for questions. Thank you.
Thank you, Paul. If there are any questions, please.
I've lost my mouse, so it's difficult to just switch back to less interesting.
Okay.
So
maybe in the meantime, I will be have one question to you. If it will be important to VLBI user or LOFAR user to use the common scale of time across the whole Europe, for example?
Not usually. For pulsar timing, that will be much more important. For VLBI, basically, all we care about is that everything uses the same reference frequency and is, yeah, within a microsecond or so. It can even be worse, and then we can phase up the array. That's good enough. However, that is for simple VLBI. If you're starting to look at things like fast radio bursts, etc., then it would be really interesting to be able to tie the measurement down to the actual UTC time, so we can compare with observations done at completely different wavelengths like optical or X-ray or whatever.
Okay, thank you. Any other questions? If not, I would like to again thank you to all our presenters for very interesting presentations. And it was the last session, first the presentation from first session. So now I think we have a break. Nicholas, can you say how much time we have?
Yeah, sorry, I was muted. Well, thanks for all those good presentation. Now I think we will have to shorten the break, and I suggest we should meet again at 2:30 CAT time, if you agree with that. So that less 8 minutes before session 2. Okay. During the break, I will share the next info shares that will happen in March. So if you are interested, feel free to register and join those next info share. Thanks. So see you at 2:30 CAT time. Okay, so it's 2:30. Well, I don't know if you can see my screen during this
yes.
second session.
Yes,
okay,
we can.
perfect. Okay, so during the second session, we'll discuss about the current situation in NREN network, and we will have a couple of presentations about time and frequency research on innovation projects. So, well, we have been mentioning several times the CLONETS projects, and also Harald talked a little bit about the TiFOON one. And so for our next talk, Vojbor will present us. Oops, sorry. Will present us those two main European projects, TiFOON and CLONETS-DS, which are gathering a big part of the time and frequency European community. Vojbor participated in several EC and Polish networking projects, Gen 2, 3, and 3. And his main interest concerns software developing technology, networking, networking technology, time and frequency transfer, of course, and optical network. So I pass it over to you, Vojbor, for your presentation.
Okay, thank you very much for this kind introduction. And let me find my presentation. Sure. Okay, can you see my screen?
Yes.
Yes? Oh, great. Okay, so I try to say a few words about time and frequency research and innovation project in Europe. So this is a short agenda of my presentation. First, I will show a very short introduction to time and frequency project and say a few words, group of potential users. And next, I will describe 3 of time and frequency project. 2 of them, TiFOON and CLONETS-DS, is ongoing right now. And the CLONETS was finished 2 years ago. So The time and frequency transfer via optical fibers project started about 10 years ago. Some of this project was national projects, some of them was international project. And generally speaking, there are two different initiatives which support this time and frequency project. First one is Horizon 2020, which supports many research and innovation activities in Europe. A CLONET project was implemented, and right now the CLONETS-DS project is implemented under the Horizon initiative. Horizon initiative also supports the MP program, which is the European Metrology Program for Innovation and Research, which focuses strictly on metrology issues. So other projects as NAFTA, IFT, often, and right now TiFOON is implemented under this program. So as you can say, we are working on time and frequency transfer via optical fiber over 10 years. A few words about groups of users. Generally, time and frequency projects focus on many groups of users like NMI, radio astronomy, telecoms, navigation, or fundamental research, or optical clocks research also. But please remember that we are very open for any new groups which would like to use precise time and frequency signals. The TiFOON project will advance fiber-based frequency transfer capabilities in Europe towards a universal tool for time and frequency metrology by developing combined time and frequency techniques with enhanced performance. So the project website can be found below. And the TiFOON project focuses on 4 main directions: the techniques for combined optical time and frequency transfer over fiber networks, human intervention-free optical time and frequency transfer, time and frequency transfer together with data common channels, and dissemination of time and frequency beyond NMI. And the TiFOON project is coordinated by NPL, and there are 15 partners involved in this project. As you can see, there are NMI, academic research, and also some NREN and industry partners. The second project was the CLONETS. The project CLONETS aims to prepare the transfer of time and frequency dissemination, new generation of technology to industry, and to strengthen the coordination between research infrastructure and the research and education telecommunication network. The project website is also on the slide. The project focuses on 4 main directions. First was definition of key technologies and trends. The second was definition of technology development roadmap and strategic agenda. The next one was identification of additional application and markets. And the last one was impact training and communication. Below is the link to the deliverables. And I think it's very interesting is deliverable D1.5. It's a fiber-based time and frequency transfer techniques, which describes and summarizes all time and frequency transfer method via fibers. So if you have time, please look at this deliverables. The CLONETS project involved 19 partners, and it was coordinating by Observatory de Paris. It's the similar as TiFOON project, combine NMI and academic and research, more NRENs and more industry partners. So the successor of the CLONETS project is the CLONETS-DS project, which focuses on establish a pan-European time and frequency reference system as a European research infrastructure to serve the European science community. The project will prepare design study for such system. And the link to the website is on the slides. The main direction of the work are scientific cases, technical design, governance and sustainability, and impact and dissemination. And the CLONETS project is coordinating by GÉANT, and the project involves 18 partners. So also NRENs, academic and research, and NMI, and some industry partners also. So generally speaking, we can say that the TiFOON project focuses more on technical aspect of time and frequency solution, and the CLONETS and CLONETS-DS project focuses on overall architecture of time and frequency network in Europe. On this site, you have link to each home pages, and you can find details about all this project. So thank you very much for attention. If you have any question, ask, please.
Thanks, Wojbo. I had one. There has been a very interesting workshop, 2 days workshop organized by the TiFOON project. Do you know if we can share the link to the videos that were recorded?
I'm not sure, but I asked NPL, and if he agree, I can share the link.
Okay, thanks. I have another question about, well, it's a more general question about where this is all going. We have been talking a lot about time and frequency services for years now, and what will be the big achievements or the next big step for time and frequency in Europe? If you have something in mind, of course.
I think right now we are all working to create a time and frequency dissemination network in Europe. We have in mind that it's not easy and it's not a short way to create such a network, but all we think that in next few years we need such a network. So the next step, I think, after CLONETS-DS and after preparing a design study, will be started implementation of such a network. In my opinion, it should be.
Okay, thanks. I don't see any other questions, so we'll jump to Joseph's presentation. So the next presentation will be a little bit longer, so it's 40 minutes, question time included. We wanted to have a bigger presentation, a longer presentation, so that we have enough time to highlight the fact that there exist many running time and frequency networks in Europe. I mean, really running, and that's why we wanted to have more time for this presentation. Few words about Joseph. He has been active in the field of photonics networks since 2003, and he was responsible for the development of a family of open photonics devices, and he currently leads the research department of optical networks in Psnc. He has been participated in many time and frequency projects and other international projects such as Complete, CLONETS-DS, CLONETS, Gen 4, Gen 3, and so on. Joseph, I hand it over to you.
So Nicholas, thank you. Thank you very much for kind introduction. Let me wish you nice afternoon. And I should be slightly speeding up. So this presentation is trying to provide some summary, and it looks like that the presentation is providing nothing. So once more. Okay. Please do you hear me?
Try to click again into the slide.
Yeah, yes. Perfect. Thank you very much for visiting. So this is some aggregated presentation, and the content in the presentation has been provided by many authors from GÉANT and NRENs, as you can see here. So I'm here acknowledging these co-authors, and let's go for the first slide. As you can probably know, but maybe someone didn't, someone don't, GÉANT would like to support the emerging time and frequency distribution in Europe, and it's aware, we heard it, that the best possible support would be into providing with dedicated dark fibers. But obviously, somewhere dedicated fibers won't be achievable or available. So it would be possible to transfer time and frequency on some lines in the GÉANT network. On the right hand, you see the new footprint of GÉANT network, where the rollout would be finished in early 2023, and these fibers are typically covered by 15 years IRU on the fibers. And as a C-band is reserved for the internet traffic flowing up to 20 terabits per second, so that it's possible to add an L-band on some links to carry this time and frequency traffic along the data. As I indicated in the previous slide that the GÉANT would like to support this, it's very, very interesting to show the strong overlap of the now rolling GÉANT backbone in the blue and the core fiber-based infrastructure for time and frequency dissemination within CLONETS project study. The overlap can be very clear seen here. And to allow this, GÉANT start the verification of this potential to perform time and frequency transport in the L-band. As it's also known, the GÉANT use the Infinera dense wavelength division multiplex systems, but unfortunately it's not possible to provide the almost standard channel 44 for the time and frequency transfer, because there is no coupling available and supported by the supplier. But the adding of L-band, and L-band means L-band including the 1570 nanometer band, is relatively easy, and L-band access ports bill is already built into the amplifier and switch cards. You can see on the figure on the right some schematic of the test where the bidirectional transmission at 1572 band is performed over some experimental setup using single path bidirectional amplifier and the laser source. We can see in previous very nice presentations how enormous stabilities it's possible to achieve using bidirectional transfer within single physical medium, together with active cancelling all the disturbances and noises. But this way of transfer has also some drawback, which lies in accumulation of a noise. And for some really long haul transfers, it's necessary to perform the regeneration. Actually, there is existing system for this regeneration, comes from the company Muquence and is designed for channel 44. And within Project GÉANT plans to perform ongoing investigation into possibilities of developing of L-band variant of this regenerator, which allows to achieve enormous length of spans. So now here I'm taking my CESNET hat. CESNET started with precise time transfer in year 2011. It's a line Prague from Institute of Photonics Electronics to BEV in Vienna. It's in cooperation with Aconet. And according to my knowledge, this is the first international line for precise fiber time transfer. It's that orange line here. And this map shows other components of the time and frequency infrastructure of CESNET, which start to grow very soon after the first line was in operation. But fortunately, the times in CESNET start to deploy not the single channel OADMs, but the group OADMs covering typically eight channels here in C-band, which allows really simply to add another frequency services. On the map on the right, you can see the present state of infrastructure. It covers more than 1,800 kilometers. Very long lines like this top blue and bottom orange are realized as alien waves, unidirectional waves, but the rest of services are truly bidirectional within single fiber, amplified by bidirectional optical amplifiers. And typical use cases, we heard it already. It's a comparison of UTC approximations. Here it's UTC of Czech Republic and UTC of Austria. Ongoing, you can see here with asterisk is comparison of UTC PL, obviously with also taking part with Psnc. And other use cases are distribution of very precise time to the demanding users, like people from geodesy, extreme light infrastructure. But we are also supporting our members, which are operating UTC-TP in the creation of the synthetic time scale. And you can see on the map inside that on lines or important lines going to national lab, there are operated multiple different technologies, our own developed time transfer adapters together with White Rabbit, and transfer is realized from the master to slave and even in the opposite direction. And you can see in the right bottom figure, these different technologies are compared to ensure that the quality of a transfer is not compromised. In the terms of coherent optical frequency, CESNET start first transmission in 2015, used these OADMs covering 8 channels, and now infrastructure, you can see it on the right. It covers more than 1,000 kilometers of fibers, and it's developed with the Institute of Scientific Instruments, which provides the ultra narrow band and ultra stable lasers, and also the active noise cancellation. What's from the operational point interesting and useful, that the major part, roughly 700 kilometers, is lit as a service. In case of this orange line, it's a fiber owner, and in case of that red line, it's even the third-party company providing bidirectional link as a service. Now we have here in operation more than 20 bidirectional erbium doped amplifiers, and this number will be pretty extended this year. And on the right, you can see the let's say original 2015 setup, deploying the time and frequency filters in the front of all the equipment, because in the time we thought that this would be critical to limit the reflections, to improve the attenuations. On the next slide, I would like to show, let's say, the later setup. And what's really interesting, and you can see that such OADMs on the plot in the, or on the photo in the middle. Here on the left, there are fibers from the line. It's a east-west fiber 1, east-west fiber 2. Here is connected the C-band, here is connected the L-band, and here is a connected telecommunication equipment, which is that dark blue box in the middle. We start rollout of new backbone in this year, featuring 400G speeds, and we heard it multiple times here. Let's say the extra deployment of OADM is something which is really bothering and which is really also risk from the operational point of view. So we are already deploying the OADM filters for both C-band and L-band. And we also finally have a very good chance to see the negative influence of amplitude modulated signals, which is time transfer. In our case, white rabbit and time transfer adapters. So our plan is definitely to move these signals out of the C-band or as an alternative, convert these signals to some phase modulation. What can I also mention here? It's that L-band is nothing to be afraid of. We have a L-band data transfer system since 2011. It was also presented on that link shown in the first slide. And this is last assisted slides. Sorry, I should mention that use cases are not also the connection of these nice ultra-stable lasers, for example, here in Vienna in BEV, but also here in Temelin, it's a sensing of a nuclear reactor, containment stability. And the next use case will be mentioned here. Our members are developing optical clocks based on a single quantum ion called InnerTrap, and the request was to establish transfer at 1458 nanometers, what can be achieved by direct wavelength doubling without using the optical comms. And on the right hand, you can see that these OADMs are becoming more complicated, but the design was done very carefully. And you can see on the left that first goes the OADMs for that 1458 transmission, which is sensitive to attenuation. Then goes the normal telecommunication splitting systems into CLL. Everything has been optimized to provide the minimal possible loss for the data traffic, because well, some excess losses obviously cause the more expensive design. And we heard it here multiple times that this actively compensated coherent optical frequency transfer can be really tremendous stable. So these are some results provided by our partner ISI, and you can see with 1 day averaging, it's really possible to go to the crazy numbers like 10 to minus 20. So that's everything for the SysNet, and let's go for to the FUNET and SCS and FUNET Finland. just for someone who haven't chance to heard extremely interesting presentation given by Jani, FUNET is using very similar scheme in that way that for long distance, this is Spokane white rabbit line. It's used as a alien wave in DWDM system, and other lines there are used specific filters which allows to perform transmission within 1610 band nanometer. And obviously you also have chance to hear about the, let's say, original transmissions between Sweden and Finland. So definitely FUNET is going to re-establish transmission to the SUNET. You can see connections to SUNET at least on 3 points and our neighboring NRENs. So my big thanks goes to Jani, and I'm trying to expedite, so all details are in the Jani's presentation. So next, according to the alphabet, we have GAR. I mentioned that some features of the GAR infrastructure has been already mentioned by Paul Bowen, and GAR use slightly different reference model for high demanding TF, and provided dedicated fiber pair under IRU, which is exclusively used by the NREN, National Metrology Institute, and maintenance of that fiber pair is managed by the CAR. And on the right side, you can see the fiber line, which frankly follows the GAR infrastructure, and it was built also in early this decade, and it's operational since 2013, where the one fiber from the dedicated pair is intended for the coherent optical frequency transfer on channel 44, and the remaining fiber, is dedicated or reserved for pre-production trials, especially in quantum sensing and quantum key distribution. And this dedicated fiber pair is mainly funded by the NREN and other programs, including European Horizon 2020, and also the regional programs. On top of this, GAR also continuously in cooperation with NREN is testing quite a bit in the productional network using unidirectional DWDM infrastructure. And yeah, sure, they are doing naturally some tests to check the accuracy which can be delivered to users, and obviously to measure the stability or accuracy in the different parts of the network. And obviously, as GAR is also GAR is primarily network operator, to understand and became familiar with the complexity of operating white rabbit devices. And in the right bottom corner, you can see some results of the time difference, and also in the night-day variation. Yeah, because this is a unidirectional transmission, so there are some variations. And here is very nice conclusion provided by GAR that the high demanding users are provided with dedicated fibers, and this is even this operation of optical coherent frequency can be isolated from the prototype services like quantum things, sensing, and so on. And this brings also some advantages that time and frequency signals are maintained by the GAR, and there are no impact on any services. And another advantage is in the independence of the life cycle, because there are definitely different life cycles of the time and frequency infrastructure and the data infrastructure. So there are no mutual dependencies, and obviously it's possible to innovate without any constraints. And GAR is working how to deliver time and frequency services to less demanding users, but with more widespreadly. You can see White Rabbit, so it's a White Rabbit technology. Here we have Psnc in Poland. Psnc is also operated quite large time and frequency network. It started 2012 with these red lines, which are using dedicated fibers. Very soon there have been added second fiber, and according this map, this red dedicated fiber-based part has been finished in 2015. Here you can see again for very long transmissions, here more than 700 kilometers, are again used telecommunication unidirectional lambdas. Actually, use cases are very similar. This time and frequency network or infrastructure connects UTC generating labs, UTC-PL in Warsaw, and UTC AOC located in Borowiec here. Into this infrastructure is already connected the lab in Toruń featuring optical clocks, and two cesium fountains, first in the Borowiec and second operated by Psnc in Poznań. In Poznań then is also located the time and frequency repository. It's passive maser connected directly to the both time scales, UTC PL and UTC AOS. Psnc is also solving another very related networks or projects. First is National Photonics Lab and National Photonics and Quantum Technologies Labs. Sorry for, it took me. And the main goal of this project is development of modern infrastructure to support these fields, photonics and quantum technologies, with attention to be given to the needs of industry. And the generation and distribution of the optical frequency is just one of sub-project of this national project. And you can see that the two original lines would be extended to the Krakow through the Wrocław, and within this project there are also international extensions considered. I think this is to the Germany through Słubice, and this one is to the Czech Republic through the Češín, and this I expect is again to reach the Vilnius. Psnc is also running next national project. It's a pioneer lab project. It will provide national platform for integration with research and innovation infrastructures, and there should be 8 specialized distributed laboratories, and time and frequency is even single distributed laboratory in this project. So this was everything for Psnc. I expect that I have seen Krzysztof and Wojbor available, so they will be available for the questions, and can go to the RENATER, National Research Education Network operator in France, which operates really really huge network dedicated for the time and frequency. It's based on the fiber shared with data traffic. The coherent optical carrier, it's transferred bidirectionally on the channel 44. And Renater is also the testing the possibilities of deployment or usage of White Rabbit as an alien wave to provide dissemination of radio frequency, time, and frequency. And on the map on the left, you can see the present state. There 2,400 kilometers are covered with international connections to NPL in UK, PTB in Germany, and NREN in Italy, where the next in yellow shown lines should be implemented. So it means before 2022, it means this year, and till 2028 is planned also big extension to the west coast, to Brest. What's also from the operational point very interesting that these transmissions are realized in parallel with Infinera, originally Coriant, which deploys Raman pumps with counter-directional pumping, with FlexiGrid OADMs and coherent transmissions. And till today, there has been reported only single incident with no impact on data traffic. Even the fibers are shared with up to 6 wavelength carrying the data. Network Operations Center is outsourced, but has a right to fully shut down any time and frequency transmission, which is available, which is industrial grade and available from vendors Buquans and Lumibird. Here on the left, you can see setup where the telecom equipment is there is added optical add-drop multiplexers allowing to inject channel 44 in the ILA sites. The time and frequency signals is removed, amplified by bidirectional amplifiers. It's here we can see it's a Lumibird. It's a sorry, wrong slide. Yeah, this is the right slide. So it's amplified, and even the optical supervisory channel is used to deliver remote control and monitoring for these inline devices. And as has been mentioned in the GÉANT part of talk, reach is extended by repeater laser stations. On the right, you can see 2 of them. Each is about 7 U rec unit height. And these repeater laser stations allow via laser locking to regenerate noisy time and frequency signals and really heal them from very low levels. You can see from even -60 dBm. On the slide on the right, you can see on the bottom, on the rec photo bottom, it's that 1U amplifier, which is residing here in ILA box, and the remote connectivity is provided by this optical supervisory channel. On the slide, you can see some operational parameters of the amplifiers, which are very small and not power hungry devices. And we are in the Sweden. I'm recalling the Janis presentation that the Sweden start transmitting the time using SDH in very early days of this, or also the Harald mentioned this in very early days. In these days, SUNET together with NetNode, which is neutral exchange operator, are doing some testing for the National Time and Pace project, which is financed by the Post and Telecom Authority. And on the right, you can see some setup which has been established because within this project there should be provide some 4 nodes which, around the country. Every node is equipped with 2 atomic clocks and is able of automatic operation. And this testbed setup on the right is using also the 1610 nanometer window. It's based from 6 hops, and in 2 spans are used 16.5 and 16.15 SFP transceivers introduced by Yanni, and even 4 hops are using the SFP directly with a circulator. This is White Rabbit ring, and they are able to achieve stability plus minus 100 picosecond over 10 days, which is pretty good. If we go for a next, what's going in the SUNET, SUNET already deployed this infrastructure shown on the right. It's for the time and radio frequency transmission from Stockholm to Sundsvall, and it goes through 10 sites and cause the regeneration using White Rabbit. It's that switch on the left bottom corner with regeneration based on OEO regenerators. According info, installation devices are already in the field and the first data are acquired. So to conclude what's happening in SUNET, we are working on this PTS project connecting these blue nodes, also to add the national UTC lab, and obviously plans are to go redundant and to connect to Finland. And we hear it again, dissemination to other location is desirable, and everyone is looking how to achieve this dissemination via even simpler nodes. And here goes SURF. From Paul, I remember very nice figures. So I definitely should mention another SURF projects. This is project for interconnecting 2 UTC labs, UTC VSL, which is National Metrology Institute, together with UTC STEC, which is European Space Research and Technology Center of ESA. And you can see on this plot, on the blue plot, that to ensure the highest possible performance, there are 2 transfers there and back from a grandmaster to slave. It's White Rabbit technology. Where the SURF is also active, it's a project of super precise or super accurate positioning, because as we know that GPS is vulnerable. We heard it spoofing, jamming, but the GPS is also sensitive in the cities where are high buildings, trees, and other sources. So SURFnet is partnering in this project where they deploy around the you can see around the highway. It's mentioned here in Delft, in Green Village. They deploy transmitters on the lamppost, and it's able to achieve the location for even moving object with accuracy of 1 to 2 decimeters, which is fantastic. And yeah, here it's so that it's necessary to achieve that magic deviation 100 picoseconds to be able to do precision, to do positioning with precision. And what's happening in the SURFnet? SURFnet see that this service is mainly for some kind of special for the special users and researchers, but see some more massive application in this timing for especially 4G and 5G timing for indoor units, which would be probably deploy in huge number. SURF is now investigating different business models from everything owned by the SURF, and the scenario where SURF is providing fibers, spectrum, and SFPs to ensure the spectral properties, and the users or researchers will provide white rabbit equipment on their self. And SURF is working on the proof of concept. You can see it on the right. It's a main protected white rabbit ring, and it would be possible to connect from in every node, every blue node with some user devices and consume with time and frequency services. So here it goes, Swiss and Switzerland. They are running Synergia project. This project connects ultra-stable laser located in Bern in METAS, National Metrology Institute. It connects it to the University of Basel, to the ETH in Zurich, and closes loop back to Basel. Use cases are precision spectroscopy and the ultra-narrowband terahertz lasers. They are using the same single fiber, single medium propagation and operation with active optical stabilization. And what's here interesting, they are using all these boxes are optical drop multiplexers for channel 7, and the gain is provided by single path bidirectional amplifiers. And this is pretty future-proof solution because it don't block any band in the C-band. So it's future-proof for introduction of the flexigrid in C-band, and any changes in life cycle or any changes in vendor with a C-band. Equipment, we can see in it, it's very, very simple, are OADMs for channel 7, which are components costing 50 euros or 100 euros. And again, you can see here ultra-stable laser and repeater laser stations for a transmission. What I'm considering extremely useful, it's shown on these slides, because Switch team went and performs quite broad verification if there are any negative influence of a coherent optical frequency transfer to the data. We know that transporters are able to monitor performance data and are counting seconds with errors, and obviously they can correct majority of these errors. And Switch team perform some, I think, 120 hours with time and frequency, with frequency transfer on, and 40 hours with frequency transfer off. And you can see influence on coherent channels on the left. Blue charts are when the laser is off. There are some fluctuations, and red sliders are when the optical coherent frequency transfer is on. Values over 1, there are positive changes, so it means more error rate minutes. Values below 1 are less error rate minutes. And on the right, you can see influence on non-coherent, 10 gigabit on-off keying, non-return to zero transmission. And what's definitely good news is that there are no uncorrected errors, like in case of Renater. And result is that there is no clear correlation that it can be stated that the coherent frequency transfer it's causing more error at seconds. There is no clear correlation. And here we have a last slide provided by UNET Norway. They are seriously exploring the need for time and frequency services with different precision. And one of big candidate is Norwegian Metrology Service. And together with them, they are identifying the needs. UNET is also about to build the next generation optical infrastructure, and time and frequency is considered in the design. So there would be deployed optical add drop filters, which add and drop L-band to allow time and frequency transfer in L-band, but they are also seriously considering the remote sensing using fibers and so on and so on. So this was the last slide from NREN situation. I again would like to say very big thanks to all the contributors. Content is theirs, and also would like to acknowledge the rest of OTFN team, not mentioned before: Xavier, Ivana, Tim, Suzanne, I think, and thank you very much for your kind attention. So please, are there any questions?
Nicholas, can you unmute your microphone?
Sorry, thanks. Yeah, there is no question in the chat, I was saying, and thanks for this very good and very interesting presentation, Joseph. So maybe I was wondering, what would you say to an NREN that is non-familiar to time and frequency services, and that is willing to maybe implement time and frequency services in its NREN? You showed us that there are multiple setups using different wavelengths and so on. What would you tell him?
Yeah, I suspect it's slightly suspicious that we are in one OTFN task, but I definitely should mention this here, that for NRENs which are not having big experiences in this field, this might look slightly confusing, because yeah, we have chance to see many possible options and ways of implementation targeting different kind of performances, from super stable to let's say quite good stable with white rabbit. And definitely these NRENs can follow the documents prepared or white paper prepared within OTFN task. And also I expect that TiFOON presentations are available. But I think that within OTFN we should more address this issue and let's say do some extension of white paper or this way to encourage these NRENs and provide some relatively simple how to guide, because you know, everyone starts Google with how to. So how to start with time and frequency in the research network. I think it would definitely help to community to have, let's say, the start, and after some experience are gathered, so it can go for more complicated setups.
Yeah, totally great. We also may say that each NREN is different. Every NREN is different, sorry, and that everyone needs to build its own dedicated infrastructure that match the end user requirements. And of course, we don't have all the same access to maybe dark fibers or dark channel, different wavelengths that we can use, but really, Joseph's presentation was here to show you that there exist many things that you can adapt to your own network, and that you don't have to be forced to use the Renate solution, for instance, or a Psnc solution and so on. Well, once again, OTFN is here to help you with if you have a question about time and frequency, that you are willing to implement it in your networks and so on. And I think you have to focus on designing your own solutions that fits your your requirements on your end users.
Absolutely confirm this. Unfortunately, there is no one-fit-all solution, and yeah, so please don't hesitate to ask OTFN for some help or materials.
Well, I would like to make a comment if I may.
Yes, please go on.
I mean, this is exactly the point. What we saw, we have different technologies ranging from precise time protocol, White Rabbit, LSTAP for timing, the comb lines, which have not been mentioned so far, to the optical carrier. All the solutions are adapted to different applications, requiring different performance level. And we have national solutions that are implemented because they tackle specific user needs. If we continue with this diverse approach, dark fiber, dark channel, blah, blah, and so on, we never make it to the European level. This is what I'm worried about. Yeah? Are we looking for adapted or a general solution for implementing this time and frequency service? This is the general question. And GÉANT is in the unique position that we can get a European solution that does not exclude any of those technologies. This is the way we. I'm deeply convinced that this is the only way to go for the European solution, that we find a way where we can, in parallel, use these different technologies that have been developed over the years to tackle the user demands.
Yeah, exactly. And the thing is that if you want to be connected to your neighbors, you have to know what your neighbors are using and why they're using such setups. And I might have been misleading, but I meant when you want to try some new time and frequency services in your network, you might not go for a whole dedicated network for time and frequency services. But of course, if your projects, if you want to be connected to other countries, to other NMI, you have to look on what has been implemented in other countries, and we need to find a united solution so that we can all be interconnected to one another in an easy way. Okay. So we might start our final presentation. That will be a Mentimeter interactive talk. Xavier, you wanted to say something?
Yeah, I would like to thank Sarah for his very nice comment, but I have the opposite question. Being in the NREN, I would say with the NREN hat, what we see is that national NREN try to address their, try to identify the requirement of their own users, and thus lead to different solutions. But it's relatively complicated for us to identify what is the requirement of the different scientific communities. So it would be also a very useful work from the different projects that we have seen before to gather all this project, to prioritize the different requirements, and try to come back to us as infrastructure providers with a kind of a list of requirements. I don't know if it's, maybe it has been already done and so on, but that was my question. Thanks.
Well, if I may answer directly, I think we know the requirements, and my approach would be to look at the highest requirement and try to avoid that all the lower requirements or the lower technologies, let's call it that way, cannot be implemented in the solution. So I would go, I would go up to the highest level, and then see, okay, if I want to, let's think the optical carrier is the highest level, because that is optical clock, fundamental physics, blah, blah, and so on. But if I need a solution where the white rabbit can co-propagate with the optical carrier.
So, but I think,
and then I have everything we need for the time and frequency service. And then we can address the question, is that possible in parallel with the data traffic? Or is the solutions, would there be a simpler solution having a dedicated fiber that offers all these time and frequency services? And Josef addressed that. We don't want to change the vendor or the optical fiber after 10 or 15 years. We want to keep that fiber forever, because the effort we have to put in is so much higher than for just exchanging the data traffic network. Yeah. So that is, from my point of view, it's just those questions we have to address, how we solve this basic problem.
Okay, thanks.
If I may, but I think that this is not in a contradiction. Harald is speaking mainly on the European level.
Yeah.
And I think that mainly Nicolas' questions were targeted to the national level, which probably it's a responsibility of each NREN or network operator to tailor it to the need of users, because it's quite difficult to reason why we are delivering optical carriers to the users which will be fine with White Rabbit. But it's obvious on a European level, it must be the highest performance possible. And on national level, it should be tailored to the user needs, because it's very difficult to justify. But
yeah, but I'm afraid let's talk about the Finnish solution with the to the VLBI station implementation of the White Rabbit that was perfectly adapted to the problem they had. Once there is a guy at the VLBI station that tells us, "Hey, I need better performance." Then you start all over again. And that hamper, in my point, I'm afraid that then we will start the national level will say, "Oh, we don't have the money for that." Yeah, we have the solution. We have already White Rabbit. Yeah, but but then you have to find money from somewhere else. You showed the slide from Sweden, where obviously the link is going up to Stockholm and further up to the north. Yeah, if in future there will be an application that is not satisfied with the performance you can provide now, you will start over again.
Okay, so from this, reasonable, it at least looks to at least reserve some bandwidth. If okay, but I don't want to delay with Menti. We should go to Mentimeter and.
No, it was very interesting question.
Yeah, very interesting. Yeah,
and I think it was very useful for others.
Thanks.
So, thanks for the answer. Nicola, you would like to start the Mentimeter? There's no any more questions?
Yeah. I'm just going to share.
I can share my screen if you want. There is there. So I send it to in the chat the URLs where we would like to collect your feedback, and I will share my screen too. So in general, in our, do you see my screen?
Yep.
In the InfoShare, what we really would like to get is your feedback, because it allows us to direct our work in the right to address your requirements. So it's very important. So the first questions is related to your organization. So after that, because unfortunately Mentimeter is anonymous for the answer. So if we collect your your organizations, therefore we can after that try to investigate and say, okay, if they would be interested with this solution, it may be Renaterga or whatever. So if we are about 50, so there is already 16 answers for now.
So again, if you want to connect to the Mentimeter, you have to connect to www.menti.com and enter the code number.
Which one? Okay, you see. Maybe it doesn't number extend a little bit. Okay, so maybe we can 20. Wonderful. Okay, so let's give 30 seconds because it was the connection time, and after that we will go to the more interesting question. 22, 23, and 25. It's almost 27. Wow, almost the half of the present from now. Okay, so let's go 28. Let's go to the next question. So when do you see your organization involved in the time and frequency technology era?
And so I don't know if you people that are answering that they plan to go for time and frequency technology area. Do you have any, if they have any projects running, or if it's already administrative stuff that was done and that you plan to implement time and frequency next year? Okay, so there are many people that have already implemented time and frequency services, so experienced end users.
So if
okay.
Okay, thank you very much. That was quite impressive to see that finally there is so many people, so many NRENs that are so many countries that is already implementing or involved into time and frequency services. And for those who would like to be involved, we as OTFN we'd be really happy to answer to your questions. So the next slide question is, how have you already identified any use cases and which one? So it's just a 1 word or 2 word about the use cases that you have already identified.
And you can also look for the words that are already entered and maybe
yes, when
some applications are already written.
Precision spectroscopy, finance, interesting, metrology, VLBI.
And we can see that there is a no, and one of the main objectives of our InfoShare today was also to provide you some example of end users that are willing to be connected to time and frequency services. So as Harald was saying, maybe the best thing you have to do if you are looking for some end users is to contact the OTFN, or maybe you can also contact your NMI, your National Metrology Institutes that may that have the contacts the contacts to research institutes that are maybe looking for time and frequency services, which will enhance their experiments. So that could be a good option.
So doesn't seem to move. Okay, I think we have reached the finish with this question, so we could go to the next one. What are the main obstacles that prevent your organization, NREN, to work on time and frequency services? Is it expertise, manpower, equipment, cost, others? That would help us to try to answer. For the cost, we could, the different NRENs that has already implement some solutions can provide some answer on this. Obviously, it's not something that we can share publicly, but I think that we can help on this. Of course, please go on.
Yeah, and I believe the least good idea would be to design your own time and frequency setups without discussing with other NRENs that have implemented time and frequency services, or discussing with your NMI. That would be the least, well, the worst idea, I would say. So you have to try to rebuild what has been implemented in what is existing. And of course, we can give you advices because we did some mistake when we first implemented our time and frequency networks. But now we have a mature technology, and we can explain to you why we built such networks and how we are sure that our data traffic are now safe and why.
What I really like is user with money, customers with money. It is always the, you know, the unicorn that you are looking at. Okay, thanks.
Yeah, and maybe for that, we in France, we had such a huge lobby for time and frequency services, and you can have a look at RefMF project and TerraFMF project, because we now have like 30 end users that are willing to be connected to time and frequency services. So those institutes are not rich customers, but if the more institutes are willing to be connected to time and frequency services, the more your government will help you build your network. And so if you have a look on existing time and frequency networks, maybe it will give you ideas to contact research infrastructures and so on, so that you can have many signatures to go for your network.
So we'll go to the next questions. Which topics would you like to be covered in the next time and frequency InfoShare? Because we plan to have a more technical time and frequency that will be given by the OTFN team. But your feedback would be very useful if you would like to have more theoretical information, time and frequency implementations that is already in production, any demonstration.
And we can also mention Harald comments, which was really relevant, but we maybe our second InfoShare would be more about why we decided to go for such solutions. Yeah, we didn't speak about the way that we are now monitoring time and frequency services and time and frequency equipment in our existing network. So that could be a thing. What not issues, but what you have to look for when you are building time and frequency networks. What redundancy? Okay. And we are, well, I just code the world national strategy, and we can even talk about international strategy, because we know that there is a worldwide race for time and frequency services. So it's even more international competition right now.
what I see is a lot of things related to demonstration.
Yeah.
There's demonstrations and so on. So that's really interesting. Okay, if there is no additional feedback, no, still. I think we have a couple of questions, and after that we will. Okay, we can go to the next slide. Which topic you would like? It's the same questions that OTFN investigate and covers in the futures. Is it, for instance, setting up a training, setting up, working on trying to implement European testbeds that could be used by the NRENs that currently investigate a new solution, pan-European time and frequency services, any other ideas?
And it could also be maybe white papers about, Xavier, you think? How to deal with your optical vendor, for instance, because optical vendor are more and more experienced with time and frequency services, and they do understand why we are talking about bidirectional propagation, and they are now more and more familiar with OADMs and so on. So, okay.
I see. Okay. Pan-European.
Mm. So there is a good demand for testbed. Mm.
Okay. I do not see additional suggestions, so I think with this, I don't know if we have another questions. I think with this we reach the end of the presentation. So thank you for this answer, and I leave to you the floor, Nicolas.
So I would like first to thank all of our speakers today. We had a very good and very interesting presentations. So we hope that you understand that there are running time and frequency networks in Europe, and that it's not something that is fictional or so on. As we saw that there are only 3 of you that haven't started your time and frequency networks. So do not hesitate to contact the OTFN projects. About what Harald was saying, so it's a very good idea to look for what are the existing solutions and try to have unification of of the techniques that should be used. We will discuss in our OTFN project to try to give you another info share that will cover the test beds and other subjects that you want us to discuss about and to detail. Sorry. Thank you all for attending this meeting, and
okay, so that is the end of the meeting. So thank you very much to everyone. Thank you once again for the very good presentation. I know that it is a lot of work. Thank you for the organization, and hope to see you in the next InfoShare. Bye.